We're starting our gas law unit, so we need to understand how gas laws behave. Some things that we're going to talk about here you should be taking notes on, and then at the end of this video I'm going to ask you questions that you'll use your notes to answer. So right here I have a box and I filled it with gas particles. It doesn't matter what kind of gas it is, they all behave the same way. And what we're going to start focusing on is pressure. We talked about pressure being force over area. Gas pressure, what causes gas pressure? That is the force of 1 billion gas particles colliding with an object. So for instance, these are moving, all gas particles are moving fast, okay? And they are colliding with each other and the walls of the container. When they collide with the walls of the container, they make pressure. So, gas pressure is collisions. When I say gas pressure, I want you to think about collisions of those particles hitting the sides of a container. Okay? So, if I have more collisions, I've got more force or more pressure. Okay, and again, we're talking about gas pressure. If I have less collisions, that's going to equal less pressure. Okay, so you guys should be taking notes on this. So, kinetic molecular theory of gases is the theory of how gases move. And they contain 5 postulates, and we say this is for ideal gases. Okay? Number 1, they consist of a large number of tiny particles in constant motion. So here's our example of a gas. And let's think that this is air, okay? And here's me. I'm sitting in this cube. And here's the air that I breathe. If they were not in random motion, all this gas would fall to the floor and I would suffocate and die. Okay, so it's really good that these particles are always in random motion. Number 2, the volume of gas particles are negligible. That means these little particles we're going to assume they're so tiny that there's really no volume. And this is important in our calculations, okay? But the volume that they take up, this whole space, the volume that they take up is mostly empty space. Collisions of these particles are completely elastic. What does that mean? That means that these gas particles do not lose energy. Okay, so let's think about this. If these gas particles, which are bouncing all over the place, they're hitting the sides of the walls, they're going crazy, if they lost energy when they collided, like say a car slows down on the pavement. Why does it do that? Because of friction. These guys don't do that. If they did, they would slow down, they'd lose all their energy, they'd fall to the ground. I wouldn't be able to breathe because all the gas would be down here and I would die. So remember, they are perfectly elastic, and that means those collisions do not lose any energy. They keep moving always and forever. Postulate number 4, there are no attractions between molecules. So a liquid stays together because those water molecules are attracted to each other. That's why water beads up. Okay, gases, however, don't have these attractions. Ideal gases, we assume, do not have these attractions. They do not clump up. If they clumped up, they'd all clump up together. They wouldn't be near me. I wouldn't have any gas to breathe and I would die. Very good that there is no attraction between these molecules. Okay, and the last one you guys already know. The temperature of a gas depends on kinetic energy, right? The temperature is a measure of kinetic energy. The temperature is measuring how fast these guys move. If the temperature goes up, these guys are moving faster, these gas particles. If it goes down, the gas particles are moving slower. Here's a balloon. So when you blow up a balloon, why does it stop expanding? Why does it only go to this size? To understand that, we need to understand pressure. Okay, so here is a guy. Here's his hand. And here's another guy. And here's his hand. And these guys are pushing on each other. Okay? If he is pushing exactly the same amount, that means our force is equal. So we're pushing equally. We have no movement. Okay, so these guys are pushing the same. As a matter of fact, if you're in the classroom, I'd stand up, somebody else would stand up, and I'd have them push me, and I'd be walking back. But then we would stop. But I'd still be pushing on someone, and they'd still be pushing on me. Why did we stop? Because the forces are equal. In a balloon, remember, we're talking about gas pressure. That is the collisions of these guys hitting the sides of this balloon. Okay, it may take them a while to get there. They may bounce around and collide into each other, but sooner or later they're going to hit the walls of these balloons. What is the force acting on this balloon that's equal, that made this balloon stop? Well, outside, so we have these gas particles, but outside we have gas particles all around this balloon. And these guys are pushing in too. And when we blow up a balloon, our balloon expands until the force inside the balloon equals the force outside the balloon. Okay? So when this balloon stops expanding, pressure in equals pressure outside. Oops, there we go. Let's start again. And that's why this balloon stops expanding. These collisions are hitting the sides of the balloon and they're creating a force. So that force is equal and opposite to the force outside of these particles hitting the balloon. And so the balloon stops expanding. What kinds of things can we do inside this balloon to get a greater pressure? Okay? What are our variables to make more pressure inside the balloon? Okay, here's our guys. Stop and think. What's the first thing we can do? Remember, we want more collisions. So what can we do to get these to hit the sides of the wall more? More pressure, more collisions. Okay? Well, what if we increase the temperature? If we increase the temperature, okay, particles are moving faster. And what does that equal? That equals more collisions. Okay, now I'm going to draw a box here, and this box is going to have 1, 2, 3 gas particles in it. Okay, now I'm going to make the box smaller. I still have 1, 2, 3 gas particles in there. Which one has more collisions per second? We have the same temperature, we're moving at the same speed, okay? So we have the same temp, so we have the same speed. Okay, and we have volume, that's big, and a volume that's small. Okay, we also have 3 particles in each. The volume that's small equals more pressure. Why is that? Well, these guys are hitting the sides, but this guy has a long way to go to come back down and hit this side. This guy can hit this side and it can bounce off and hit the other side much faster because it has less distance to travel. So if I have a small volume, I have more pressure. So volume, temperature, we have one more thing that we can consider. Let's say I have this box and I have 1, 2, 3 particles in that box. This is the same box, and so we have the same temperature. We have the same number of particles, or we have the same temperature and the same volume. And I'm going to put in 1, 2, 3, 4, 5, 6, 7, 8. Okay, what do I have here? I have more particles, but we don't talk about particles. We say I have more moles. Remember, moles is how we count particles as chemists. More moles equal more pressure. Why? Because I have more collisions. Okay, let's write that better. Oh, no. More collisions. So, remember, when I say gas pressure, what causes pressure? You say collisions. More collisions, more pressure, more collisions. So we've talked about boiling of water and how our normal boiling point is at sea level. Things boil differently at the tops of mountains, and this all has to do with pressure. So remember, when I have a liquid, I have vapor pressure leaving, and boiling is when the external pressure equals the vapor pressure. Okay. So why do things boil at sea level differently than they boil on top of the mountain? And do they boil at a lower temperature or a higher temperature on top of the mountain? Okay, well, let's talk about the difference in the external pressure. What is the external pressure? External pressure is just the air pressure. Air pressure. That's external pressure. Okay? And that's in your blue book. These are notes we took before. But let's look at this in more detail about the gas. What's different down here than up here? Well, you've heard people say there's not a lot of air at the top of the mountain. This is actually true. So down here at sea level, we have our air. And as we go up a little higher, they get more spread out and then more spread out until there's hardly any air at the top of the mountain. So again, lots down here and then almost none up there. So if I have a vapor pressure here, and let's say our external pressure is 1 atm is beating down on here, and that holds the water in. That means my vapor pressure is 1 atm, okay? And I need a certain temperature to make this equal, okay? Well, up here I only have half an atmosphere of pressure. ATM is atmospheres, and that's pressure, and that's pushing down on the top there, okay? That means my temperature can be lower because I only need half as much pressure pushing up to boil, okay? So if you lower the external pressure here, you can make water boil at a lower temperature. And we're going to watch a video on that. Okay, so we talked about how water boils at 100 degrees Celsius. That's at sea level. But if I lower the external pressure, the air pressure above it, I can get it to boil at a lower temperature. This video is going to put this flask of water in a vacuum chamber or a bell jar. And there, what that is a device where you can remove all the air around it, thereby lowering the pressure that's pushing on that water. So let's watch that.
Air pressure. In this demonstration, we'll show that. We have some water at 80 degrees Celsius. It's been heated up on a hot plate. We're going to take this water and put it inside a vacuum chamber. Turning on the compressor, we'll pump out this air above the liquid water. You can see the result here. At 80 degrees, the water erupts in a full boil. What's going on here? To understand how this could happen, we need to consider what is going on at the surface of the water. Normally at sea level, for example, there is significant air pressure from all the air molecules above the liquid. This pressure keeps the majority of the liquid molecules from flying apart, as shown in the blue at the bottom of the beaker. However, if we remove much of the air above the water, in other words, create a low pressure environment for the beaker, these liquid water molecules are not pushed on as much and now have enough significant kinetic energy to fly apart, and the result is water vapor filled bubbles, or boiling water.
So now here's some more bell jar experiments that I would have shown you if we were in class. And remember, the inside, let's see if I can get this going here. Right
in a demonstration of Boyle's law,
the inside, we're pumping out the air pressure. So the air pressure pushing down on this balloon is going to be less, which means the balloon can expand.
we'll place the balloon in a vacuum bell jar. We'll apply a vacuum, which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. We will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases.
So when they're releasing the vacuum, they're letting the air back in. So we have more outside air molecules pushing down on that peep or pushing down on the balloon, which is why they shrunk back down.
As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar.
So shaving cream is another type of substance that has a bunch of air bubbles in there. So inside each little air bubble in this shaving cream is 1 billion particles of air molecules hitting on that outside little bubble. Okay, so right now it's not moving because the pressure inside the little air pockets here equal the pressure on the outside, but they're going to remove this air. So this pressure will go down.
Shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
Okay, so for this next video, we're going to talk about pressure and temperature. Remember, the collisions inside the balloon are due to the gas inside the balloon hitting the walls. And how many times do they hit, how many collisions are happening is definitely dependent on temperature, because temperature is how fast they're moving. The faster things are moving, the more they're going to hit the outside of those walls of that balloon, and it's going to have more pressure in the balloon. If I cool it down, those molecules will slow down and the pressure inside the balloon will be lower. Why? Because slower moving particles cause less collisions. So let's watch what happens here.
I'm going to dip the balloon in the liquid nitrogen
Liquid nitrogen's really cold.
and ask what happens to it.
So it's cooling down those particles in the balloon.
Shrinking. Why? Because it's cooling the air in the interior of the balloon. And in fact,
It's causing less
kind
collision.
of crackling and becoming that's what happens to helium.
What I want you to notice here is when he takes it out, the balloon gets bigger again. What tells you that the balloon would get bigger if you're thinking about collisions? Well, when he takes it out of the liquid nitrogen, the air inside the balloon is getting warmer, so the particles inside the balloon are moving faster. They're having more collisions.
Start off a little bit bigger. We're actually running a little low on liquid nitrogen there.
Now watch what happens when he takes it out. It went right back to its normal size when he took it out. The temperature inside the balloon went up. We got more collisions, which increases the pressure inside and made that balloon expand back to its normal volume. Okay, here's a faster demo. Again, I want you to think about those particles inside of air inside the balloon. We're going to pour liquid nitrogen over this balloon, and if we pour liquid nitrogen over the balloon, what happens to the speed of the molecules inside the balloon? Which means what's going to happen to the volume of that balloon? Liquid nitrogen's ice cold, but now the balloon's warming back up, so the air inside the balloon is moving faster, causing more collisions and making the volume increase back to its original size.